In this video, we will look at another type of compound inequality, the OR. The OR requires at least one is true. As we solve these, we will remember that we have to flip the symbol. Again, when we multiply or divide by a negative. As we graph these, we may find we have two parts of a graph because we only need one to be true. To represent two parts of a graph, we use the symbol, looks like a horseshoe, which is read union. Let's take a look at an example where we use that symbol in interval notation. In this first OR inequality, we start by subtracting the 7 from both sides, giving us 4x is less than negative 12, and then finally dividing both sides by 4 to get x is less than negative 3. Or we solve the other equation by adding 8, giving us negative 4x is less than or equal to negative 12. To get the x alone, we simply divide both sides by negative 4. And notice we've divided by a negative, so we flip the inequality symbol to get x is greater than or equal to 3. Again, we will graph these by floating the individual graphs above a number line. X is less than negative 3. With an open circle at negative 3, we want to go down. X is greater than or equal to 3. Because it's or equal to, we have a closed dot at 3. Greater than means we go up. Because this is an OR inequality, we only require one of them to be true. At least one. So wherever we see a graph, that's going to make it onto our final number line. So we have an open circle at negative 3 going down, and a closed circle at 3 going up. The only thing that doesn't make it into the final graph is the space in the middle where neither one works. In interval notation, the graph starts at the left, smallest value, negative infinity, up to 3. Infinity is always curved, and 3 is curved because it's not equal to. Then, to show it's a second part, we use the union symbol, or the horseshoe. The graph starts again with a closed bracket at 3, a square bracket, all the way up to infinity, which is always curved. And this is our interval notation. Let's take a look at a second example that's a little more involved, but we do the same idea, requiring only one graph to be true when we use OR. We can start this first one by subtracting 4x to get the variables all on one side. 4x plus 9 is less than negative 19. Subtracting 9 from both sides gives us 4x is less than negative 28. Finally, dividing both sides by 4 gives us x is less than negative 7. Or, in the other equation, we must start by distributing to get 12x minus 16 minus 2 is less than or equal to 8x minus 50. Combining like terms, 12x minus 18 is less than or equal to 8x minus 50. Move the variable to both sides or to the same side by subtracting 8x gives us 4x minus 18 is less than or equal to negative 50. Adding 18 gives us 4x is less than or equal to negative 32. And dividing both sides by 4, we find x is less than or equal to negative 8. On a number line, we can graph the two separately, starting with the negative 7, open circle. Less than means we go down. From negative 8, with a closed circle, less than means we go down. We only require one graph to be true, which turns out to be the bigger graph from negative 7 on down. The only part not making the final graph is the part that has nothing. In interval notation, negative infinity to negative 7.